Hello everyone, welcome to my channel Enlightening Data Science and welcome to this course on SAX-VSM time series data classification. So as the amount of data collection is increasing and the rapid rise in usage of sensors like IoT devices to collect data, time series data is becoming more and more popular. So in this course, I will show you what time series data is all about, what are the characteristics of time series data, and how we can use this method, very powerful method called SAX-VSM, which stands for Symbolic Aggregate Approximation, and vector space modeling to analyze time series data using classification. So let's start. So the agenda of this course is that I will start with what is time series data, then I will describe time series data analysis, time series data analysis types, then I will show you the characteristics of time series data and what is time series data classification. Then I will show you a shapelet transformation method used in time series data analysis. Then there is another method called bag of words for time series data analysis that I will show. And then I will discuss this method algorithm called SAX-VSM, Symbolic Aggregate Approximation and Vector Space Modeling, and how we can use it to analyze time series data. Then a part of SAX-VSM, another algorithm called piecewise aggregate approximation that we use for dimensionality reduction to reduce noise in time series data. As time series data has a lot of noise, so we need to reduce the noise before analyzing it. So we use piecewise aggregate approximation that I will show you. Then I will show you the difference between dimensionality reduction and numerosity reduction. And the another method embedded in SAX-VSM is called vector space modeling, or TF-IDF, that we use. So I will show you that as well. And finally, I will show you the method called cosine similarity that we use here to basically uh, identify labels for the testing data once we have the labels for the training data. All right, so before I move further, do subscribe to my channel Enlightening Data Science for videos like this, and for the next videos I'll be making on data science. So make sure you don't miss them. So you subscribe to the channel. All right. So what is time series data? Time series data is a sequence of data points collected at regular intervals over a period of time where the order of data points is crucial for understanding trends, patterns, and variations that, uh, that may exist within the data. And this is also known as time-stamped data. Time series data is a data collected at different points in time, such as GDP of a country by year or stock price of a company over a period of time, or even a heart rate recorded at each second. So that's all time series data. Time series is a sequence taken at successive equally spaced points in time. Thus, it's a sequence of discrete time data. Example of time series are heights of ocean tides, counts of sunspots, and the daily closing average of Dow Jones Industrial Average that we see in the stock market every day. So the right chart, top right chart, is the stock price of Apple company, and it's all time series data because it's a data collected over a period of time. And only after we plot that data, we can analyze the time series data using data visualization. And the chart on the bottom right side is showing time series data for multiple variables. So in one chart we can also put several variables. So in this case we are using heart rate, blood pressure, and respiratory rate uh, collected over a period of time. So any that data that is collected over a fixed frequency time period, it's time series data. So time series data analysis, it's used for non-stationary data changing over time. Industries like finance, retail, and economics use time series analysis as currency and sales are always changing. Time series analysis is ideal for forecasting weather changes, helping meteorologists to predict weather report and future climate changes. So, one very important aspect of time series data analysis is forecasting or predicting what will happen in the future. So, we have the data collected, and then we can use several machine learning methods. Some popular are like SARIMA, which stands for Seasonal Autoregressive Integrated Moving Average. Uh, that's one method that we can use to forecast the future data, and that's very much used uh, in weather forecasting. So that's how we can see the weather for the next 1 week or few days. So some examples of time series analysis include weather data, rainfall measurements, temperature readings, heart rate monitoring, brain monitoring, quarterly sales, stock prices, automated stock trading, industry forecasts, and interest rates. So here on top right you see snowfall in New York City uh, by plotting data collected from 1992 to 2010. And we can see that it has a definite seasonality, which means that snowfall peaks during some time period, especially during winter, and then it drops during summertime. So we can see the the peaks are increasing over the last from 1992 to 2010, suggesting that the amount of rainfall uh, has been amount of snowfall has been increasing in New York from 1992 to 2010. So that's how we analyze time series data. And in the bottom right chart, it's a random data with a lot of noise, which is the black uh, black data points, and then it's showing some trend line. So if a data has a lot of noise, we can plot a trend line in time series data to analyze it to basically identify the trends, patterns, and relationships, and then generate insights from that data. So time series data analysis types are classification that we can use to identify and assign categories to data, which is the topic of this course as well. We can also use curve fitting to plot data along curve to study relationships of variables. We can use descriptive analysis to identify patterns in time series data like trends, cycles, or seasonal variation. We can also use explanative analysis to understand data and relationships within it, as well as cause and effect. We can also use exploratory analysis to highlight characteristics of time series data. And another powerful method that I just described is forecasting to predict future data. And this is based on historical trends. It uses the historical data as a model for future data, predicting scenarios that could happen along future plot points. Intervention analysis that we can use to see how an event can change the data, and segmentation where we split the data into segments to show the underlying properties of the source information. For example, a graph on your right side is showing visitors to this very famous Yellowstone National Park here in California, US, and it's showing the number of visitors visiting that park from 2014 to 2016. And again, this shows a seasonality where we can see that people visiting the park uh, peaks during summertime when there's no snow, so that people can easily visit the park, and the number of visitors drop to almost very minimal during the winter time. So that's the whole idea of this chart. So what are the characteristics of time series data? Number one characteristic is autocorrelation, which is the similarity between observations as a function of the time lag between them, An autocorrelation of +1 represents a perfect positive correlation, while an autocorrelation of -1 represents a perfect negative correlation. It can also be referred to as lagged correlation or serial correlation, as it measures the relationship between variable's current value and its past values. So you can see the chart that I put here for autocorrelation that we can use to identify when it's a perfect positive or perfect negative correlation. Then another important characteristics of time series data is seasonality, which refers to periodic fluctuations in business areas and cycles that occur regularly based on a particular season. A season may refer to a calendar season, such as summer or winter, or it may refer to a commercial season, such as the holiday season. So it shows the airline passengers from 1950 to 1960 with seasonality, especially during the holiday time. Airline passengers increased during that time. Another characteristic of time series data is stationarity, which is a time series status when its statistical properties such as mean, variance, and covariance remain constant over time. Time series with trends or seasonality are not stationary because these factors affect the value of time series at different times. So to determine if a time series is stationary or not, we can use several tests that are available to look for specific characteristics in the data, and two of those tests are augmented Dickey-Fuller test (ADF) or Koski-Phillips-Shim test that we can use for identify those statistical properties in time series data. And these tests are used especially when we are building a machine learning algorithm on time series data. And before that, we need to identify whether the time series data has a stationarity or not. So there we use a lot. So the chart on this slide shows the first is a stationary time series, and the second is non-stationary time series with time-dependent mean, and the third one is non-stationary time series with time-dependent variance. So what is time series data classification? Well, time series classification uses supervised machine learning algorithms, and supervised machine learning is basically where we have labels already done for the training data, and then we can use those labels to predict labels for the testing data. If the data is already labeled, that's where we use supervised machine learning. So it's used to analyze multiple labeled classes of time series data for the using the training data, and then predict or classify the class that a test data set belongs to. This is important in many environments where the analysis of sensor data or financial data, which are both time series data, need to be analyzed to support a business decision. Some types of time series classification methods. Number one is distance-based approaches, like Euclidean distance or Hamming, Manhattan, or Minkowski distance, and this machine learning algorithm called k-nearest neighbor, where we basically identify which data point belongs to which cluster by using several different clusters and then assigning the data point to the nearest cluster using the distance. That's that. And then we have another powerful method called dynamic time warping, where we measure the similarity or distance or dissimilarity between two time series uh, um, data. So that's where we use TTW. And then another classification method used for time series data is Shapelet, that we use to identify data shapes in time series subsequences. Um, Example, ECG shapes to identify heart diseases. Because patients with that disease have specific characteristics in their heart rates, and we use those shapes called shapelets to to determine if that person has that disease or not. Model ensembles, where we use collection of classification models, several different classification methods are combined, and that each perform their own class discrimination on the dataset. Dictionary approaches, where we use the number of occurrences of a particular shapelet in time series, and bag of patterns algorithm that look at amplitude of a time series signal within some specified window of the data and apply a simple transformation to the signal to represent the mean of the signal within that window. This feature then becomes the basis for the dictionary that is used to train a classifier. Another method is interval-based approaches, where we split time series into distinct intervals, and each interval is used to train an individual machine learning model or a classifier. And now, with the artificial intelligence and deep learning methods, where we used neural networks that has multiple layers of neurons or perceptrons, these models are more complex and in fact more powerful, with many more parameters, like millions or billions of parameters, than other types of algorithmic models. So the initial layers of the deep learning method encode shapes, while the latter layers encode representations that can be discriminated into classes in the final layer. So if your time series is a very big data set with millions of rows collected over a lot of time like big time period, then deep learning method is very powerful to identify hidden trends and patterns and relationships. And some of these methods are based on transformers that are powerful enough to generate some very useful insights from time series data, and even use time series data using deep learning to make very accurate predictions or do forecasting. So Shapelet transformation algorithm extracts shapelets from a dataset of time series and returns the distances between the shapelets and time series, the original time series. So a shapelet is defined as a subset of a time series that is a set of values from consecutive time points. The distance between a shapelet and a time series is defined as the minimum of the distance between this shapelet and all the shapelets of same length extracted from this time series. So the most discriminative shapelets are selected, which means which are very unique in shape and which are very distinct from other shapes. They are collected, and all of it is done in Python using this package called transformation.shapeletTransform from Python library called pyts. So here in this chart, you can see the four more discriminative shapelets identified from this whole time series. And these shapelets are designed to be distinct in their characteristics from all the other shapelets, meaning they will have their different mean and variance, and that's how they are different based on their statistical properties. What is bag of words for time series? Well, several algorithms for time series classification are based on bag of words approaches, which is a sequence of symbol is transformed into a bag of words. So the idea is basically to divide the whole time series into subsequences and assign alphabetical characters to each of those subsequences using bag of words. So bag of words extracts subseries using a sliding window and then transforms each subseries into a word using piecewise aggregate approximation and symbolic aggregate approximation algorithms that we will show you in the next few slides. And bag of words transforms each time series into a bag of words. The sliding window can be controlled with the size and step parameters. The sliding window determines how long is each subsequence. And the length of each word can be set with size parameter, while the number of bins parameter controls the size of the alphabet to discretize time series. And the numerosity reduction parameter controls the removal of all but one occurrence of identical consecutive words. So the idea is to generate distinct uh, sequence of words using bag of words for time series. So here we will describe the method of this that we use for classification called symbolic aggregate approximation in vector space model, which stands for SAX-VSM. It's based on two techniques. The first is symbolic aggregate approximation, where we which assign high-level symbolic representation of the time series, and the second is vector space model, which is based on TF-IDF weighting scheme. So by using SAX, the algorithm transforms real-valued time series of a single input class into a collection of SAX words or bag of words. Next, by using TF-IDF weighting, the algorithm transforms these collections, one collection for each of the input classes, into class characteristic weight vectors, which in turn are used in classification for the testing data, and that is all built upon cosine similarity. Basically, identify how similar the labels of the training class and the testing class are, and then uh, generate labels or classes based on that similarity. For an unlabeled time series, which is the unlabeled testing data in our case, the predicted label is the label of the TF-IDF vector, which is coming from the training data set that we have already labeled, and that gives the highest cosine similarity with the TF vector of the unlabeled or the testing data time series. So this graph on your right shows you on the left is the TF-IDF vector for each class in training set. In training set we had two classes, class 1 and class 2. And for simplification, imagine in a machine learning model you have two classes or binary classification, yes or no, or 0 or 1. So similarly here, we assign the bag of words to each of those classes and then generated their TF-IDF vectors. And the graph on the right side shows the cosine similarity between the TF-IDF vectors for each class in the training set and the TF vector for each sample in the testing set. And then we will assign the labels using this similarity, cosine similarity. So symbolic aggregate approximation, or SAX, is based on a high-level representation of time series and vector space modeling based on TF-IDF weighting scheme. SAX discretization is performed by dividing Z-normalized subsequence into W equal sized segments and then computing a mean value for each of the segments and mapping it to symbols. Z-normalization is also known as standardization, which is a data normalization technique that we usually used before building any machine learning method like this one as well, where we use classification. And it basically transforms value to have a mean of 0 and a standard deviation of 1. It means it normalizes the data, so the data becomes a normal distribution basically, with mean 0 and standard deviation of 1. It's a pre-processing step that is used quite often in machine learning and time series structural pattern mining. The algorithm consists of two steps. It transforms the original time series into the piecewise aggregate approximation or PAA representation, and then it converts the PAA data into a string. PAA, or piecewise aggregate approximation, offers simple and efficient dimensionality reduction, especially if time series data has lots of noise. So one aspect of time series data is that when it is collected, it usually has a lot of noise, and that noise we tend to minimize when we analyze the data, and that we use through this method called piecewise aggregate approximation, where we do dimensionality reduction or minimize the noise in the data. We also z-normalize the data before converting into PAA by dividing the area under the normal distribution or the z normalized subsequences into A equal areas. So here is the one working of SAX-VSM algorithm for time series classification algorithm. So you can see on the left side the classifier training is being done, where all time series of class 1 and class 2 are converted into a single bag of words, which generated one bag of word per class. And next we calculated the TF-IDF weighting and then applied it, which resulted into two TF-IDF weight vectors characterizing each of the two classes with their respective mm, numerical numbers for class 1 and class 2. And then the classification of the unlabeled testing data time series uses the weight vectors that we just obtained at the training step to compute the similarity using cosine similarity between the vectors in testing set and the vectors of sex words frequently obtained by processing the unlabeled time series with exactly the same sex discretization parameters used in training. And the classification label is assigned by identifying the cosine similarity or the weight vectors, which yields the maximal cosine value. And the maximal cosine value meaning that the weight vectors of the training data and the testing data are similar. So whenever they are similar, we know that the label that comes from the training data is the label to be assigned to that class in the testing data when cosine value is minimum. So piecewise aggregate approximation that is part of this method SAX-VSM, it basically uses the time series with a high sampling rate or which is very noisy, and then in order to reduce noise we use this method where we take the mean over back-to-back points and then decreases the number of points and reduces noise while preserving the trend of the time series. So here we can see in this graph the blue curve is the original time series, and then we use the piecewise aggregate approximation to reduce noise while preserving the trend, and then the resulting uh, time series curve is the orange line that we see. So you can see it preserves the trend, however it reduces those peaks and those troughs, and overall it reduces the noise in the data. Piecewise aggregate approximation of time series approximates a time series x, for example, of length n into vector x bar of any arbitrary length, where the length of the vector is always less than or equals to the length of the original time series. And in order to reduce dimensionality from n to m, we first divide original time series into m equally sized frames, and that's how piecewise aggregate approximation reduces dimensionality by using the mean values of equal sized segments. So to each segment we identified the mean of that whole segment and then use that mean to reduce dimensionality through PAA. So PAA method downsamples original time series, and in each segment, where each segment has a fixed size, the mean value is retained. So the chart on the left side, we see a time series called C is represented by PAA, where we have the mean values of equal segments. And in this example, the dimensionality is reduced from n equals to 60 to k equals to 6. So instead of the whole curve, we have those 6 segments, and each segment is represented by its mean of equal length. The segment is of equal length. And on the chart on the right side, we see the time series is discretized using SAX method, and there that's how we assign the labels or the bag of words to each segment for analysis. So this chart shows you how we can convert one time series on your left using symbolic aggregate approximation, where we assign those bag of words to that time series data. So you can see the SAX approximation method divided the whole time series into three bins. The bottom bin is all A alphabet, the middle bin is all B alphabet, and the vertical bin is all C alphabets. So that's how it converts the original time series into bins and to a string, and the whole time series is now represented by this string called ACDBBDCA. So in Python, we can do this all, implement this algorithm using python.approximation, where from which we can import symbolic aggregate approximation. And here's a simple example where we converted the time series X uh, and using transformer method, and the whole time series is now converted into bag of words. So this is how it is implemented. Here we show you the discretization via sliding window, where each segment that we, or each subsequence of the time series that we divided using the sliding window approach is assigned bag of words or a string. So the first sequence is, for example, ACF, then we have FDF, then FCA, then ABF, then FFF, and then the last segment is identified as DCA using this method of discretization via sliding window. Here I show you the piecewise aggregate approximation representation. So how a raw data on your left side with some noise is converted into 7 segments of equal size but with different means. So that's how we reduce noise or reduce dimensions in the data using piecewise aggregate approximation. Another demonstration, on your left side you have time series and the piecewise aggregate approximation, which we use to convert that time series into 9 segments of equal length, and then we used symbolic aggregate approximation distance computation, where each of that segment is converted into some word. This is part of the algorithm implementation. So symbolic aggregate approximation, discretization, numerosity reduction is basically where we use the neighboring subsequences that we extracted from the whole time series using sliding window, how similar they are to each other. So if same symbolic aggregate approximation words or strings or alphabet characters, they occur more than once consecutively, then instead of placing every instance into the resulting string, we only record its first occurrence. So that's how we reduce the dimensions or the noise using numerosity reduction. So basically, numerosity reduction is a data reduction technique that reduces the volume of data by representing it in a smaller format. And there are two types of numerosity reduction methods called parametric and non-parametric. This method speeds up the algorithm besides finding variable length motifs and anomalies. So motifs are some trends or some patterns in the time series data that we identify, and anomalies are unusual occurrences that basically show you that something unusual is going on in your time series data. And one example of anomalies is when financial institutions identify credit card fraud, because those are unusual patterns in your daily or in your general spending of or your usage of your financial instruments. So anomalies and motives are two important aspects in time series data. So the process here, for example, S1, we had two consecutive occurrences of words AAC and AAC. So numerosity reduction deleted one AAC2 because both of them are occurring consecutively and they are similar, so it removed one of that part. However, if it occurs later on, for example AAC6 and AAC7, so there also we removed AAC7 and kept only one occurrence of that uh, bag of word. So what is the difference between dimensionality reduction and numerosity reduction? Well, in dimensionality reduction, data encoding or data transformation are applied to obtain a reduced or compressed form of original data. In numerosity reduction, data volume is reduced by choosing suitable alternative forms of data representation. Dimensionality reduction can be used to remove irrelevant or redundant attributes, and numerosity reduction is a representation technique of original data into smaller form. In dimensionality reduction, some data can be lost which is irrelevant. However, in numerosity reduction, there is no loss of data. Methods for dimensionality reduction are wavelet transformations and principal component analysis, or the PCA method that we use in machine learning. And the methods for numerosity reductions are regression or log linear model, which is a parametric model, or histograms or clustering and sampling methods, which are non-parametric methods. The components of dimensionality reduction are feature selection and feature extraction, while the components in numerosity reduction are none, but the methods that ensure reduction of data volume are often used in numerosity reduction. Dimensionality reduction leads to less misleading data and more model accuracy, while numerosity reduction preserves the integrity of data and how data is reduced. It shows that in action. So we discussed, mentioned vector space modeling, that is part of the SAX-VSM algorithm. So vector space modeling is also called TF-IDF. It's basically a vector space that contains a collection of objects called vectors, which are numerical representation of words, sentence, or even documents, while a simple vector like map coordinates only has two dimensions. Those used in natural language processing, where this method TF-IDF is used a lot, there we can have thousands of coordinates or dimensions. So the vector space model is an algebraic model that represents objects like text as vectors, and that makes it easy to determine the similarity between words or relevance between a search query and document. Cosine similarity is often used to determine similarity between vectors. So that's the whole purpose of the algorithm SAX-VSM, where we have the labels coming from the training data, and then we identified the TF-IDF vectors on that data in training data, and then we calculated the TF-IDF vectors on the testing data, and then we calculate the cosine similarity between the TF-IDF of training and testing, and then the one with the minimum cosine is similar, and if they are similar, then the label coming from the training set is the label that we need to assign to the unlabeled testing set. So that's how TF-IDF is used. So TF-IDF stands for term frequency and inverse document frequency. And TF-IDF is a weighting scheme that assigns each term in a document a weight based on their term frequency or the number of times they appear. And the inverse document frequency, IDF, is basically a way that we minimize the occurrence of one item multiple times, like I showed you in the last slide, where we use numerosity reduction to remove consecutive occurrences of sequences of words, so that they are not they do not you know overpopulate in the data. So the terms with higher weight scores are more important. TF-IDF weighting scheme, here we have TF T comma D equals to N T comma D, where TF TD equals to term frequency for a term T in document D, and NTD is equals to number of times where a term T occurs in document D, and inverse document frequency is equals to the log of the number of documents that is divided by the number of documents containing the word, and term frequency is equals to number of repetitions of a word or a sequence of word in a document divided by the number of all the words in a document. So as I just mentioned, IDF, or an inverse document frequency factor, diminishes the weight of terms that occur very frequently and increases the weight of terms that occur rarely. Example, most occurring words like is and as, of, etc., that occur quite a lot in English comprehension, and while doing natural language processing, we need to remove the weightage of those terms that basically have uh, no emphasis in language processing. However, they are part of grammar, so they are used most often. So this method, cosine similarity, that I mentioned, it measures the similarity between two vectors of an inner product space. It is measured by the cosine of the angle between two vectors and determines whether two vectors are pointing in roughly the same direction. It is used most often to measure document similarity in text analysis or natural language processing. For two vectors A and B, cosine similarity is based on their inner product and is defined as the following formula, where similarity A comma B is equals to cos theta, which equals to the dot product of A and B, and divided by the uh, dot product of modulus A and B. So the rules of cosine similarity is that it measures the degree to which two vectors point in same direction, and when vectors point in the same direction, cosine similarity is 1, and when vectors are perpendicular, cosine similarity is 0. When vectors point in opposite direction, cosine similarity is -1. As you can see in the graph in the bottom part of this slide, and the chart on the right side, you can see there are several vectors A, B, C, and D, and we calculate the angles between them to to eventually find the cosine similarity, and then find how similar they are uh, using these rules. Alright, so these are some of the references. Now I'll show you the demo in a Python Jupyter notebook for where we implemented this algorithm. So here is the time series data classification. So we implemented all these packages. Uh, and then I am using symbolic aggregate approximation vector space modeling method, implementing it. So this is an example data set that we can use. It's like a toy gunpoint data set that we can use from built-in Python package. And then I used the SAX-VSM transformation using window size, word size, and number of bins, where we basically divide the whole time series into subsequences using sliding window and discretization, and then assigning bag of words to that. And then after that, it is implemented using two classes, class 1 and class 2. Uh, we calculated the vectors for each class of the training set, and then used that on the testing set, and then found the cosine similarity. So this is how the plot looks like. On the left side is the TF-IDF vector for the training set, and the right side is the cosine similarity between TF-IDF vector for the testing set. And then we assign labels to the unlabeled testing data. So binning continuous data into intervals can be seen as an approximation that reduces noise and captures the trend of a time series data. The symbolic aggregate approximation algorithm bins continuous time series into intervals, especially transforming independently each time series into a sequence of symbols called alphabets or letters. And this example illustrates that transformation that I described in the slides. So here we are using the binning strategy in symbolic aggregate approximation. So it divided the whole time series into three bins. The bottom bin is all A characters, the middle is all B, and the top is all C. So this has three bins, and we assign symbols to those three bins respectively. So what is the bag of words approach? So here I show you the implementation of bag of words algorithm in Python. So I loaded some data set which is built in Python package of bag of words, and then use the parameter of bag of words, implemented bag of words algo, and then plotted the result. So here you can see the whole time series is divided into multiple subsequences of bag of words. So each shape is basically a different bag of words that we can use using this method. Another popular time series classification method is shapelet transformation. So here I implemented shapelet transformation in Python, and you can see the whole time series is now divided into four more discriminative shapelets that are distinct in their statistical properties, and that we can use to divide this time series data. Well, bag of patterns approaches are common in time series classification, and the bag of pattern algorithm uses a sliding window to extract subsequences from time series and transforms each subsequence into a word using piecewise aggregate approximation and symbolic aggregate approximation algorithms. So it is it is designed to transform each time series into a bag of words that we can use to derive the frequency of each word for each time series using weight vectors. And here the bag of patterns algorithm is implemented using Python. We use the same built-in dataset and then implemented the bag of pattern algo using its parameter like window size, word size, bins, and numerosity reduction. And after implemented, we can see the whole result for the two classes, class 1 and class 2, that we had in the original time series. And this is how the result of bag of words look like, where we have frequencies of each sequence of words, and then we can use those frequencies to calculate the weight vectors, and then we can use those weight vectors to identify labels on the testing data. Alright, so that was this course all about. Hope you liked the course. Don't forget to subscribe to the channel if you want to stay tuned to watch videos like these or many other topics in data science. And I hope you enjoyed. And time series data is definitely is prevalent everywhere in each and every field nowadays, and it is important to understand how we can use several data analysis methods or like classification that we can use to generate insights, trends, and patterns from time series data. Thank you very much, and God bless you all.